People pointed out yesterday that the video that I showed doesn't directly showcase breaking encryption overall. And I would say that that's true, right? If I had showcased yesterday in the video breaking encryption, utilizing RSA, utilizing the method that breaking RSA encryption, utilizing the method that people would want me to utilize, that would qualify me for the Riemannian $1 million prize, right? And so, yes, no, I did not showcase solving the $1 million Riemannian challenge. And so what I can showcase here for you is a very simple example of utilizing swarm intelligence for breaking XOR encryption, which is a far easier task to do overall and to showcase, and it wouldn't be like $1 million prize, right? And then so within this, kind of the bottom line, like I think that people approach these problems and all of this wrong, right? Just flat out. Like, what do I do differently than other people within this? Like, I don't have an end goal. That's my secret, right? Like, plain and simple is that I do this purely for the exploration aspects and things that like shake out like this, like being able to break XOR encryption, for example, are things that just shake out on the side, right? It's not a goal for me to be able to do this or develop algorithms that can, but it's just working through physics, things like that. It's when you work through like physics problems, then you start dealing with like implications of working through those physics problems, right? And that's how I look at this overall. Like someone asked me, like very directly, like what am I hoping to solve within this? I'm like on my channel, etc. Like I'm not hoping to solve anything, right? Like overall, like I don't have a end goal. Like if I solve X, then it's complete. To me, it's like for 99% of my life, there's been questions like philosophical and scientific and physics related questions that like if you explore like to a certain path, like to the end of the path, then it's like you get like 96% of the way there, and then like that's the end of the path, right? Like because nobody knows. It's like, well, we don't know. We can't test past that. And then now like there's areas where we can test better than we could ever tested before with regards towards physics overall. And then if you have that actual understanding, like to me, like this is the greatest time ever to be alive to me. Like we have so many new doors that are opening and have been opened that people don't understand overall, right? So before I dive specifically into exactly what this is doing and how it's doing it, like I want to dive more into how it's doing it and how I develop this, right? And so to me, it all boils down to physics, right? And then so if you understand and you start to like dial physics within this, you can cheat. And like, so if there's like any sort of like magician magical things that I'm doing whatsoever, my secret is just plain and simple, utilizing and understanding physics and how physics plays into every single one of these equations, right? And then so kind of within that, one of my latest things that I've discovered within physics is that there is a entropy speed limit as a universal rule. And this is applicable to digital systems, physical systems, etc. Right? And then so I tested across multiple different spaces: Euclidean, fractal, hyperbolic, high dimensional lattices, as well as physical thermodynamic systems. And then those include copper, aluminum, glass, etc. And then what I find within this is that there are very, very clear limits to how entropy works, right? And how much entropy can grow. The more that entropy can grow in a system, theoretically, the faster the system could learn, right? And then so what we see here is a very interesting pattern here. Look at the numbers here on the left-hand side, right? First of all, so we can get and determine the scale on these graphs, because it's going to be very important as we go through these graphs. But look at hyperbolic compared to literally everything else, right? I mean, so everything else, even the high dimensional lattice, which is like the second best, is peaking at like 500, whereas hyperbolic is peaking above 3,500, and then our fractal is like let's call it 100, right? And then now let's go and we'll look at other situations. So our fractal's actually at like 120 is what we can see. But then everything else on this spectrum, look at it, it's capping at like, we'll call it 10. And then, so that's Euclidean space is included within that, which is very important. And then all of these thermal spaces that I'm testing. And then here we go, right? This, again, this is capping at 10. And then so Euclidean space is 0. And then quantum space is 1. Thermal space is capping different ones. Are like, so thermal copper would be the best at almost 10, right? And then same thing here, different test. We go through different systems, and then thermal copper again, right? Thermal copper at 10. And then so pretty consistent there. But 10 compared to 3,500, right? And then so this, why I outline this and why this is important to me is that these are cheat codes when you put them together, right? So if I want to have a system converge quickly, and I know that I want like an instantaneous answer, I put it in hyperbolic space because it's like literally it's the speed limits of the universe, and I can prove it out via full mathematical equations based off of all of these experiments that prove that this is a speed limit of the universe, and it's dependent on the space and the dimensionality of the space. And then so by putting it into a bunch of dimensional spaces, like in hyperbolic space, it allows me to get access to more compute than I would otherwise. I can cheat the system by utilizing things like this, right? And then so that's putting together these like individual cheat codes essentially gives us this swarm intelligence for breaking XOR encryption, flat out, right? And then so essentially what this is doing is it's an agent-based search with swarm queen optimization, and then I do single byte and multi-byte keys, so I'll show you there. And then it goes through. The bottom line, I'll explain how this framework works to you very simplistically, right? So you take a magic box, and then within the magic box, we put a problem within it. And then that problem in this instance is encryption keys. And then I say, here's the encryption keys, and then the solution to these encryption keys are somewhere within the box. I'm going to place both of them in the box, right? I don't know where they are in the box, and I don't know what the solution is, but here's the problem. And then so I'll put it in there, and I can tell you where the problem is in the box. Now go find the solution based off of the problem. And then so the swarm queen in this instance gets and starts off with like that full map, right? So then she understands and she's getting like fed inputs that allow her to visualize the map of this space. And then she's in charge of the agents that then go through, and they have individual rules in this instance. So in this instance, they're trying to solve for numbers within and sequences of numbers, right? So then she says, like, she has teams of agents then. So like agent team 1, agent team 2, 3, 4, right? And then she gets fed those individual inputs back, and then she has the full map. And then so she's guiding based off of the full map, and then based off of her updated understanding of the map in order to guide the agents to best try to solve these problems flat out, right? And then what happens is that she's going to converge, and then if the swarm queen converges 100%, she's solved it 100%, right? And then I'll go through and I'll show you two instances here of solving 90% and 99%, basically. And then so we go through, and then all of this is so. I laid out essentially the framework for you, right? It's Monte Carlo simulation. You put it into a box. The agents are searching this simulated search space. All of this is utilizing and playing off of physics, right? I'm essentially within this, I'm putting in a bunch of cheat codes based off of physics. So the agents themselves are cheating physics because I'm cheating compute by essentially making each individual agent like a little piece of compute, and I can distribute that compute. So rather than like, let's say that it's 16 cores, right? So you could like the most common way to do it would be to distribute across 16 cores. So you get like 16 parallel calculations, right? But then what I do is I split each one of those individual cores further into individual tiny agents. So I'm splitting the cores into, say, 1,000 agents instead of 16 cores, right? And then so 1,000 individual tiny agents making up all of the cores, which are making up all of the compute. So I'm splitting that compute like 1,000 times, right? And then essentially what this is it's a brute force operation, right? So and it's very important within this. I'm utilizing and the kind of the visualization method that the Swarm Queen is utilizing in this instance is harmonic resonance. She's getting back, and her map and how she visualizes all of this is like sound waves essentially, and then like echolocation is where I started thinking of this from, right? Like how bats work, and then that's like her environment is bat like echolocation, right? So she's getting bounce signals back from the agents, and then I have 1,000 agents that are going out and bouncing the signals, right? And then so they go and they bounce the signals, and then whichever signal is the best, that's what gets calculated throughout that. And it's very simple as to how that actually breaks down, right? And then what happens is that they're able to find and locate essentially the key in this particular instance, right, by bouncing these individual signals. So they converge, and then she converges up to, in this instance, 90%, right? She's 90% accurate, like by the end of it. Where you see like some of the testing, I could have ended earlier. Like if I ended early, she would like this would have converged better. So pointing that out, and that's a common thing with swarm algorithms and swarm intelligence. Like I just wanted to showcase this for you by stepping it out to 50, but I could very easily make this better if I stopped it at 5 or even 3. We would get a perfect score on this. But I wanted to show you an example of solving like 90%, right? And then so in this instance, the solution is 1, 2, 3, and then 90% gets us, they find 1, 2, 2, right? And then this is what they're finding. So 1, 2, 2 is you can see like what they're aggregating as the score in. And then so each one of these individual agents or the agents groups is going through and then finding these scores, right? And this like these graphs are like the echolocation that the Swarm Queen is getting fed back, right? And then so the Swarm Queen is building these graphs essentially and operating off of this. And then so this is simple 1 byte and having it not converge, right? But so from here, all I need to do is make a few simple tweaks and a few simple like calculations to the dial, right? And then I'm going to increase the strength of this encryption quite significantly. So I'm going to use a 4-byte keys. So it's going to be a digit from 0 to 999, and then I'm going to use four bytes total, right? And then so we'll go through, and then much harder calculations, much more agents. They're pinging a lot more, right? But I also do some tweaking to the algorithm to make sure that we're getting better convergence in this instance. And then so you see again, but same thing. If I had stopped it here, like or at 3 would be the best, like 98%, right? Like, and then we go through, and our end convergence in this instance is 96%. So I could have stopped it earlier and gotten even better, but 0, 74, 210, 145 is correct. And then so basically like above 95% convergence, like it's pretty much like guaranteed. Right? And then you can see here's exactly how it's calculating and then going through for each one of these byte keys, right? So then for 0, the best candidate is 0. For the 74 and this second one here, we can see that it's taking the best candidate like here at the very top, right? Whichever one is the very top, that's 210 is here. That's why it's converging at there. And then 145 here, right? The top ones. And so we can see where it's picking it and getting this data from. It's essentially taking its best ping back. Like it's so like for each one of these, like here's 1,000 echoes. Which one is the best echo? And the model is converging off of that and taking it in, right? And so here's the encryption key, like and then so here's what this key is. See, like all the CU 8 star 7T, you know, blah blah blah, and then there it is. I can de-encrypt it like this, right? And you see these are running 0 seconds, 0 seconds. Like it's not long to find these solutions, 4 seconds on the first one, right? So I optimized on the second one, but you're still talking like, I mean, seconds, right? And then there it is overall. And so bottom line is, like, to me, it's people put a lot of faith in things that they don't understand and don't understand physics a lot overall. And I think that's what, you know, trips people. To me, this is all math and all physics, and there's no way to around that ignore it, right? Like, you can try to philosophize around it, you can try to BS your knowledge around it, you can do all different types of things, but it all comes down to physics and math, and the best way to get that is to experiment with it over and over again, right? Like, I build these models out up and down every single day because that's exactly how I increase my knowledge of physics and math, like, and especially when it comes to these things overall. So just pointing that out. This is open source, this swarm intelligence for breaking XOR encryption. If you want to break XOR encryption, don't tell me, do whatever you want with it. And if you like this type of content, please like and subscribe. Thank you very much.